Hello and welcome to the second installment of our AI lectures in Pathfinding. Previously in this series, we looked into graph representation of the level layout. In case you haven't watched this part, it is strongly recommended that you watch it before proceeding to this episode. You should have also implemented your own graph and get something like this. In this part, we will make our spider follow the route. This route will initially only include two nodes, the initial and the destination, but it will start moving. So, waypointing is a technique that allows non-player characters to follow a sequence of positions, which will be coded as a sequence of C-vector values. Just as a quick reminder, C-vector contains x, y coordinates. In our program, the waypoints are defined as a member variable waypoints or M waypoints, which is an STL list of the C-vector values. You don't have to add this variable to your code because it's already there. The waypoints will be created in the semi-game on left button down function, which is called by the framework each time the user clicks the left button of the mouse. This function is called with two parameters, x and y, which of course specify the position of the click. And the first step here is that we pack these two numbers into a C-vector value v. Now, the first check is if the move is legal. What it means, if the user clicks inside the wall, of course, the spider shouldn't follow this direction. So here is the code. We use the variable called tile layout, which defines the layout of our level. This is how this variable is defined in the code. This is an array of arrays, and each character in this array of arrays describes one tile position in our layout. So axes represent walls and spaces represent empty space to which the spider can walk. We have to convert the coordinates x and y, which are normally provided with a pixel precision. We have to divide it by the size of a single tile, which is 64 by 64 pixels. Now, the first real step is to find the initial node, the first node. This first node will be the node of our graph, which is the closest to the current position of the spider. This will also be the starting point for our pathfinding algorithm. So here is the code, but maybe it's not the best solution.
Use the force, Luke.
Okay, let's use STL. This is the STL code. As you can see, it's much more compact, but it may also seem a little bit more complicated maybe, but if you have experience with STL, there is nothing really challenging in it. So first of all, we use the min element, one of the standard functions called in terminology of STL an algorithm. Min element finds of course a minimal element in the collection. The collection we take is the M graph. We start from the beginning and at the end, so we take the entire collection. But our search for the minimum element is not a trivial one, because the minimum element in this context means the element that has the minimum distance from this node to the current position of the NPC or the spider in our case. So the function min element uses a special predicate or simple algorithm to compare between two elements of the collection. Please remember, these are all template functions, so the function, the min element algorithm, does not know what kind of a collection it looks for. So it doesn't know that this is a node collection. This means that we have to provide our own function to define how to compare two nodes in the special way that this test is always won by the node that is closer to the spider. And this is very nicely solved in STL based on C++11 new, reasonably new syntax by so-called lambda function. A lambda function is a function that is written in line, in place, as a part of a function call. So we have the function min element, opening bracket, 1, 2, the third parameter of this function call is another function which is entirely written inside this broader function call. And what this function does, first of all, it will use the context of this, so it will have a free access to our mygame object. Okay, so that's to provide some context of execution for this function. The function must take the references to two nodes, n1 and n2, and if n1 is smaller than n2, n1 is smaller than n2, it should return true. And how it does it? It calls the distance function, so calculates the distance between the position of the node n1 and the current position of the NPC, the spider, and calculates the same for the second node, compares them, returns the value. All the rest is provided automatically by the min element algorithm. But this algorithm returns a value which is a little bit tricky. It's so-called iterator. To convert iterator into a number, we can simply take this iterator, I first called here, subtract from it the iterator representing the beginning of the graph. And in this way, the n first will contain the offset or the index of the minimum node in the graph. Okay, so I'm not sure if it was really a simple thing, but the code is short and elegant, and it's really a good thing to learn something about STL. And besides that, oh, just trust me, I'm a programmer. This piece of code just works. So what we have done so far, we have identified the index of the node which is closest to the current position of the spider. Now we will do the similar thing with the last node, the closest to the destination point of the spider. The code is pretty much similar, but instead of taking the position of the NPC, of the spider, we take the V, this is the click point pointed directly by the user. So we have the first node, we have the last node. The next thing is remove the current waypoints and reset the NPC. This is necessary in case of the spider already having some set of waypoints. So if the set of waypoints, if the list of waypoints actually is not empty, we will clear it and additionally stop the spider. So if the spider is walking somewhere, we will stop it and ask it to keep in place. And the final thing is, well, call the pathfinding algorithm to complete the waypoints. We have here a small problem. We don't have yet a pathfinding algorithm, but I will propose a partial solution of this problem in the very next slide. So for now, just imagine we have a pathfinding. So the pathfind algorithm takes 4 parameters. The first parameter is the graph, okay, so a collection of all our nodes. Then the pathfind algorithm needs to know what's the first and the last node, but this is what we have just calculated here in our function. So first, last. And the final parameter, path, will be the result. As you can see, path is a vector, so a sequenced collection of integers. So it can provide a pathway, for example, from node 3 to node 5 to node 7 to node 8, something like that. The final point here is that we have to do some small conversion. The pathfind function does not know about the coordinates of the nodes. The pathfind algorithm only returns the indices of the nodes, and the waypoints are not the nodes, the waypoints are the coordinates, xy positions. So we will iterate for every position in the path returned by our pathfind algorithm, and for each of them we will take from the graph the position of the node and push to the back of the waypoints list. In that way, we will convert the result received from the pathfind algorithm. It will be converted into XY positions. And the final waypoint we have to add, we have to push at the very back of the list. It is the V, it is the destination point, the precise position of the user click. That's all to the on left button down function. You might try to recreate this function as a programming exercise, or you can use copy and paste, because what I'm giving you here is the code ready to use. But there's one more thing that we have to think about. For your code to work, you also need to start with the pathfind function. We can use a stub function, so a function which doesn't implement the full algorithm yet, because the full algorithm will be only discussed in the next episode of this algorithm, but something very, very, very simple now. Pathfind with all those parameters, we will just push the starting and the destination or goal nodes to our resultant path and return true to say, yes, this was a success, the path was found. The pathfind function could also return false in case there is no viable path from start to goal, but this is not our case. Now we just provide a quick stub for you to use. And that's actually everything that you need to implement in this step. So you are now ready to go ahead to the practical activity, and this is because another important piece of code, the code that makes NPC, or spider in our case, to follow all those waypoints, is already implemented for you in the see my game on update function. But anyway, this is this function, and let me spend a minute or two on quickly discussing what's in this function, particularly that waypointing is quite a useful functionality for any game, even if it is not a very intelligent, very smart movement or pathfinding. If you don't want your NPC just to go a very simple route, but a little bit more complex route created of a number of waypoints, this is the solution for you. All right, so the NPC in each step, in each update cycle, so this is something that the NPC will do many times per second, like 60 times per second, for example. So the first thing to do is to test whether there are any waypoints available. If a waypoints list is empty, there's nothing more to do. But if there are any waypoints, then the second test to do is to find out whether or not the NPC or the spider is in motion. If it is not moving, or it's moving very slowly. It's to cover a situation in which speed is just above 0. Okay, so if it is not moving, then we should make it move to the first waypoint by setting the speed to 500, setting the animation to walk, and the displacement vector or the relational position of the waypoint front position, so the first waypoint in the waypoints list, its position in relation to the current NPC position. This value will be used to set up the direction and rotation of the movement of the NPC. So the NPC will start walking towards the first available waypoint in the list. The next thing is to find out if perhaps the moving NPC, and it should be moving by now, has it or has it not passed the waypoint. So we calculate again the displacement of the current waypoint, so the position in the front of the list of waypoints in relation to the current NPC position, and we apply the dot product test on this value. The dot product test will tell you whether the waypoint is in front of you, or rather in front of the spider, or perhaps behind the spider. If it is behind, so the dot product is less than 0, then we should stop the movement. And we do it by, first of all, removing the current waypoint from the list, so it won't be anymore followed. So the first position of the list will be removed, and this is exactly what the pop front function in STL does. Then, if there are no other waypoints, so the list of waypoints after this operation is empty, then we'll set the animation to idle. And whatever happens, we'll set the velocity to 0, 0, so the NPC will stop and reset its rotation. And that's the end of the onUpdate function, but please note that if this happened, that the NPC has passed over the waypoint, then in the very next onUpdate cycle, so like 1/60th of a second later, all these tests will show that we have a waypoint and the NPC is not moving because we have set it here to motionless, not moving. Therefore, the very first or consecutive waypoint will be taken from the list in order to start moving towards this waypoint. And this is how waypointing works. You should get a result which looks more or less like this. So it's not yet full pathfinding. Obviously, we haven't yet implemented the pathfinding. And we only put the initial and the final node into our waypoints list. So this movement is now very simplified. But first of all, it's now programming time. Okay. So please get back to your Visual Studios, finish your code, and then watch the next installment of this lecture, in which we will eventually implement the actual pathfinding algorithm called Dijkstra algorithm. And for now, I thank you for watching, and goodbye.